Thanks for the introduction. Thanks for the invitation. So as you can guess from my affiliation, I belong to the applied world. And as you can also guess from the title of the talk, I would like to speak about some, in my opinion, interesting facts about convex relaxations of graph isomorphism problems. I would like to start with an example, and there are actually plenty of such examples in, for example, in computer vision. Let's say I have two objects that I can endow with some structure, and I would like to find the best structure preserving map between such objects. And just to be concrete, let's say I equip these manifolds with a distance. For example, I have a manifold X with a distance dx and another manifold Y with a distance dy, and I would like to find a mapping between these two spaces that minimizes this distortion of the metric. Okay. And actually, it appears to be a very hard problem, and there are many works, including my own works, on not only on how to find such maps, but also how to represent them. Because in practice, these shapes can contain hundreds of thousands and maybe millions of points. It is a very tough computational problem to find these maps. And it is very disappointing that there are many works to attack these problems that work exceptionally well, but there are no theoretical guarantees. Usually they all boil down to some non-convex optimization problems, so the only guarantee you can get is that you converge to a local minimum, but you don't really get the best distance preserving test.
Is there some reason why the colors are reversed? One has a blue left hand and the other has a right.
Well, if you are matching distances, for example, there is no way you can resolve this symmetry. So I will speak about symmetries in particular. So symmetries are one of the problem that flags the easy solution.
So you did it on purpose.
Yes, exactly. Okay, so and basically it is very appealing to model this problem with graphs. So I can think of these manifolds, and of course there are many other examples of problems where the need to find such structure preserving correspondences arise. For example, in neuroscience, people try to match brain networks. They can be represented by graphs. So basically, I'm interested in, given two graphs, finding an isomorphism or some approximation of the isomorphism between the graphs. So I already need to apologize for the terminology. I will use the terminology that is very frequently used, or I should say abused in the applied community. Usually the applied community speaks about graph matching problems, but they refer vaguely to graph isomorphism problems of different kinds. So I will distinguish between the graph isomorphism problem, which asks whether there exists an isomorphism between two graphs, and I will be talking about weighted undirected graphs that I will be representing using the adjacency matrices A and B. Of course, these are two symmetric matrices. And exact graph matching problem will be actually to find such an isomorphism, versus inexact graph matching, where the graphs might not be exactly isomorphic, but then I will be interested in finding some minimum distortion isomorphism in some sense. Okay. So if I formulate this as an optimization problem, basically I can think of my isomorphism if I assume that the graphs have the same number of vertices. My isomorphism can be represented as permutation matrices. So I will be minimizing some distortion between A and the adjacency matrix B multiplied by the permutation from the left and from the right. So this permutes the vertices of the graph. I will be minimizing this over the space of permutation matrices. And actually this is a funny problem, because it is known to be NP. It is not known to be NP complete, but there is also no known polynomial time algorithm for solving it. So it looks like it is a hard problem, but probably there are some cases where this problem actually becomes trivial. I will mention just a few. And it appears, at least in the applied community, it appears that among the set of many heuristics that have been proposed for solving such problems, convex relaxations work extremely well. So I will just do some algebraic manipulations to this problem. So first of all, I will use here the L2 norm. And if you go back to the example of pairwise distance preservation, actually this L2 norm has a lot of geometric meanings. Basically, I'm trying to minimize some L2 energy of the discrepancies between the pairwise distances between the points on my two shapes. Well, because the L2 norm is invariant to orthogonal transformations and permutation matrix is orthogonal, I can transform the problem into this form. And then I can replace my space of permutation matrices, which is a very ugly space to do optimization on. I can actually replace it by its convex hull, what is called the Birkhoff polytope. This is the space of doubly stochastic matrices. And this objective is convex. The set, the feasible set is also convex, so I get a quadratic program.
So,
yes, please.
Do people also study the case in which A and B don't have the same number of vertices?
Yes, yes, of course. For example, doing partial matching, but I will keep it simple. Of course, it is a much more interesting case to discuss. So there, if you have partial matching, then you can show that it is NP complete. The problem is NP complete. Okay. But I will stick to the full matching case where basically I have the same number of vertices, and I'm interested in finding the bijection between the two graphs. So this is the typical convex relaxation that is practiced, and it worked. It works really well. It can actually, with some tricks, it can scale to sufficiently large graphs. But in general, the solution of this problem, of course, is not a permutation. You will get some doubly stochastic matrix, which nobody guarantees it will be a permutation. So you need to project it back, to quantize it back onto the space of permutations. And this can be done by, for example, by finding the maximum inner product between the solution of the convex relaxation and a permutation matrix. And it appears to be what is called the linear assignment problem. There is a family of algorithms, usually known as Hungarian algorithm, that can solve this in polynomial time. And actually, you can think about a much simpler projection here that I will mention in the sequel. So there are way better ways of doing this projection that also work in practice, but I will again stick to this very simple formulation. Okay. So the general recipe that I'm going to follow, I will solve this convex relaxation of the problem. I will refer to this problem as graph matching, and again, apologies for the abuse of terminology, and then I will do the projection. Okay? And of course, the question I would like to ask, what is the relation between this pi hat, which is the result of the projection, and pi star, which is my isomorphism that I'm trying to find? So, well, obviously, pi star is a solution of the convex relaxation. It is actually a global minimum, because it will give me 0 here. It is also a doubly stochastic matrix, but of course the converse is not true. I might get some doubly stochastic matrix here, P star, that will fall into some wrong Voronoi cell in my space of permutations that will give me some non-zero distortion. And here I must admit, I must express my frustration. So I asked many people some people from that are supposed to be experts in graph theory. Probably I asked the wrong people, and they were not able to tell me much about what can I guarantee. what relations can be guaranteed between these, the solution of the relaxation and the true isomorphism. Of course, there are some graphs for which trivial things can be said. For example, if I have a bipartite graph or a tree, there are trivial algorithms that can give me the exact isomorphism. But in general, it looks like not so much is known about the relation between these two problems. Okay? So what I will try to show you is some, I would say, elementary analysis of this problem. So maybe I will be saying trivial things, but at least I hope to convince you that it leads to some interesting observations. Okay? And of course, please be welcome to challenge anything I'm saying. Yes?
So what about if you have a Cayley graph? Because there is a lot of literature also on group bias.
Well, again, I will be happy to hear more about specific structures of graphs, but I started with a problem where I have a graph that sort of represents a discrete metric space, or something that, for example, is sampled from a low-dimensional manifold, maybe with smoothness properties or bounds on dimension and curvature. So I don't think there are any results that make use of such properties. And I would be, of course, very happy to see how these properties can be used. Of course, there are many classes of graphs where a lot can be said, but for general graphs, it is not so obvious. Yes, please.
Do you need the isomorphism to be unique?
No. So I will basically all the problems will arise from cases where the isomorphism is not unique. Okay. Okay. So first of all, the relaxation space itself. So the relaxation space itself that people are using is the convex hull of permutation matrices. This is the tightest convex relaxation that you can think about. But I will be using a different relaxation. So I would like to drop the non-negativity constraints, and I would like to drop one of the either row or column sums constraints. So instead of talking about doubly stochastic matrices, I will be talking about what I probably should call pseudo-stochastic matrices. So they have the rows sum to 1, but there are no non-negativity constraints. So it's an affine space. It's a much coarser relaxation of the original problem. So there are no overlapping constraints, and there are no non-negativity constraints. And from practical perspective, this can help a lot to solve these optimization problems and maybe to scale to larger ends. So I will be considering this relaxation, and I will define a particular class of graphs where this relaxation, I will show it, will give the exact isomorphism. So I will be giving a spectral characteristic, and by spectral I'm referring not to the spectrum of the Laplacian of the graph, but the spectrum of the adjacency matrix. And actually it would be interesting to find correspondences between these results to the spectrum of the Laplacian, because obviously the Laplacian is well more researched, and also it can be easier the connection to the underlying smooth structure, for example, a smooth manifold. Is probably much easier to obtain. So I will call a graph friendly if its adjacency matrix has a simple spectrum. And another funny condition is that no eigenvectors are orthogonal to a constant vector of 1s. So basically, sort of, so you can think of the projection of the eigenvectors on 1 as sort of the DC, speaking in signal processing terms. So there are no eigenvectors that have 0 DC component. Okay.
This excludes the regular graphs.
Of course. This excludes the regular graphs. So I will say something about how to get rid of this condition, but this excludes the regular graph, exactly. So first of all, this friendliness property actually has an almost trivial connection to symmetry. It is very easy to show that friendly graphs are asymmetric, or meaning that they have trivial automorphism group. And actually, it's very easy. So if I assume that my adjacency matrix admits this unitary eigendecomposition, and let's say pi is some non-trivial symmetry of this graph, so pi a equals a pi, well, then then basically for every I, AUI equals lambda IUI, these are eigenvectors and corresponding eigenvalues, I can multiply both sides by pi, and I get this. But because pi A equals A pi, I get this. And this means that pi UI is an eigenvector of A corresponding to the same eigenvalue as UI. Now, because A was assumed to have simple spectrum, this means that pi UI is equal either to plus or minus UI, because I'm assuming, of course, that the vectors are unit. So they must be linearly dependent. But we also assumed that pi was a non-trivial symmetry. This means that there will be some eigenvector for which pi UI equals to minus UI. And because of that, 1 times pi UI will be equal to minus 1 time inner product with UI. But pi is also a permutation, so of course it has unit sum of the columns. So from these two results, I'm getting that the inner product of UI with vector of 1s equals to 0, which of course contradicts the assumption that this graph was friendly. So basically this property is actually giving me the fact that friendly graphs are asymmetric. And of course, the converse is not true. You can think of a regular graph that is asymmetric, for example, the fruit graph, or there are many graphs that you can construct with probably about something like starting from 10 vertices and more. But I shouldn't be getting into this point, but I can argue that such graphs are not so frequent. And I would like to keep off any arguments regarding some natural distributions of graphs. But I will touch this point, and if I forget, please remind me. Okay, so I will show 3 results that are basically versions of this result, but the main result is very simple, and I will show you an elementary argument to prove it. Basically saying that if we have A and B two friendly isomorphic graphs, then the convex relaxation will give the exact unique isomorphism. We know that it's unique because friendly graphs are asymmetric. And of course, because I'm already getting the exact isomorphism from the convex relaxation, it will survive projection in exactly the same form. So basically, after projection, it will still be the same isomorphism. And here, actually, well, we need to check 2 assumptions. So checking whether the graphs are isomorphic is hard. Obviously, it is the hard problem that we're trying to solve by resorting to the relaxation. But checking friendliness is easy. It's a spectral property. So what I will do in practice, I will check friendliness and then solve the relaxation. If, as the result, I get 0 distortion, this result guarantees me that what I got is a unique isomorphism. Otherwise, if I got non-zero distortion, this result guarantees me that the graphs are not isomorphic. Okay? Any questions so far? So let me show you a very elementary argument to prove this statement. So I will assume 2 graphs A and B with some isomorphism pi star relating between them. And these graphs are friendly, so pi star is unique. So we are interested in solving this convex quadratic program, which is over-relaxed. It is a bigger relaxation that is typically used in practice. And of course, I know that pi star is its global minimizer. If I substitute it here, I will get 0. What I would like to show that this minimizer is unique. So what I will do first, I will reparameterize this problem by, first of all, substituting, instead of A, I will substitute this form, and then multiply everything by pi star transpose. Again, the L2 norm is invariant to orthogonal transformation. So I will get this. I will call this matrix P pi star transpose. I will call it Q. It's also a stochastic matrix, and in particular, it will also admit this space of constraints. So I can easily do this reparameterization, and because of the particular form of the constraints, here on the right-hand side, I have the same vector of 1s. I can reorder these constraints in any order. In particular, I can also put P pi star transpose here. So I'm getting this problem. I will write it in terms of this new matrix Q. And the global minimizer of this problem now is Q equals identity. It's sort of assuming some canonical numbering of the vertices of both graphs. And again, I need to show that this minimizer is unique. Okay? So, of course, I can formulate first-order optimality conditions for this optimization problem. So the Lagrangian, the derivative of the Lagrangian with respect to Q has to be 0 with some set of Lagrange multipliers alpha. And after simple calculus, you will be getting this expression. Now, I will substitute this eigendecomposition for B, okay? And then multiply both sides by U, your transpose, you will be getting this. So I will be, again, using a different set of variables. So I will be now expressing my unknown in the eigenbasis of the adjacency matrix. So I will call this matrix F, okay? And gamma will be the set of Lagrange multipliers in the eigenbasis of the adjacency, and V will be the projection of vector of ones on U, okay? And remember, because we assumed that our graphs are friendly, no entry here is 0. Okay? So basically, I need to solve this system with respect to F and gamma. And obviously, what I'm going to show that this system is full rank. So I can write it in coordinates. You see, it's a complete square here. So I can write it in coordinates like this. It will be Fij multiplied by the square differences between lambda I, lambda j, plus Vj gamma I. Okay. So if in particular I look at the diagonal of this system, I'm getting Vi gamma I equals 0. And I know that no Vi is 0, so this means that gamma is 0. I can eliminate this second term from the system, and I'm getting this. Okay? Now, because of friendliness, I know that for any I distinct from j, lambda I is also distinct from lambda j. So this means that F is diagonal. Okay? And because I also know that Q has all rows summing to 1, I can write this in terms of F like this. Okay? So I'm getting Fv equals V. Now, because no V equals 0, the only diagonal matrix that will satisfy this is the identity matrix, obviously. Of course, because F is I, then Q is also I. Okay? So this basically shows that I have a unique minimizer, that the system is full rank. Questions so far? Well, at this point you can argue that this is completely uninteresting, because if I have matrices with simple spectrum, I can simply compare the two eigenbases of the two graphs and get the exact permutation. Actually, I will get the permutation up to a sign, but I can then just cancel the signs and this will give me the permutation. But I will try to convince you that this way of looking at the problem will still give some results that probably are more difficult to obtain if you just try to compare the eigenvectors. Okay, so one such result would be, let's see if this result is stable. Let's do a perturbation to our graph. So instead of friendliness, I will assume a slightly stronger property. I will assume that the spectrum is separated by some delta, and that the projection of the constant vector on my eigenvectors is bigger than some epsilon. Okay, so it will be a strongly friendly graph. And then basically I can show that for two graphs A and B that satisfy this stronger property, that they're approximately isomorphic with a constant rho. And by approximately isomorphic, I mean that there exists an isomorphism that has distortion smaller than rho. So then if this rho is smaller than some constant that depends on delta and epsilon, then the distance between the solution of the convex relaxation and the true isomorphism will be bounded in the infinity norm by 1/2. Okay? And obviously, if it is bounded by 1/2, then it means that you can even naively quantize this result by simply taking all the entries that are smaller than 1/2 to 0 and bigger than 1/2 to 1. So this projection will give you, obviously, the exact isomorphism again. And the proof is very simple. Basically, you have a full rank system, and you put these constraints to guarantee that a sufficiently small perturbation will keep it full rank, and then you use regular perturbation theory to actually tell how the solution is going to change. And the expression here is ugly and depends, unfortunately, on the size of the graph. But at least it shows that the problem is stable. And actually, it would be very interesting to do some more delicate analysis here. For example, if you can tell something about the spectral properties of your perturbation, like something that only affects higher frequencies of your graph, and for example doesn't affect the core structure, maybe you can put some better bounds here. So of course it is very important in practice. Well, and here again, I will not check this property. I will just verify that this strong friendliness property is satisfied, and then I will solve the relaxation. If the result is smaller than the bound, then I have a theoretical guarantee that my solution is the exact isomorphism, or not exact, is the approximate isomorphism that is the global minimum. Otherwise, this result guarantees me that the graphs are not row isomorphic. Okay, the same story we had with the case of the exact isomorphism. Any questions so far? Please.
So, do you know what rho actually is?
Well, there is basically this ugly expression. I can show it to explicitly, but I don't think.
Do you know what the explicit function is?
Yes. Well, it will depend on epsilon and delta, some powers of epsilon delta and some power of n.
Okay.
So I don't remember it exactly, but at least I don't find too much insight in the specific expression.
I'll ask them. Go ahead.
Yep. Okay. Any other questions? Okay. So some experimental validation of this result. So maybe these sort of plots will be very intuitive to people who work on matrix completion or compressed sensing or these sort of problems. Basically, they call it in that community phase transition plots. Basically, I randomized 1,000 strongly friendly graphs and then added different levels of noise to each of these graphs. So basically, the noise, just to plot everything on the same axis, I'm normalizing the noise by this specific bound. So for every graph, of course, it will be a different constant. So the noise is normalized to this bound. So it means that when I'm adding noise of 1, normalized noise of 1, the bound is supposed to hold, and then the bound is, there is no more theoretical guarantee. Well, actually, I was expecting to get that, because of this very crude analysis, I was expecting to get something that is very far from being tight, but actually here it appears that there are some graphs that start violating this bound already for a very small amount of noise. And then, of course, as you increase the amount of noise, then there is higher and higher probability of not being able to recover the isomorphism. And actually, maybe I'm cheating a little bit here, because it might happen that the noise I'm adding will actually create me an isomorphism that is better than the ground truth that I assumed. And I, of course, have no way of checking it, because it would require solving the exact or enumerating all the local minima of this objective function.
What's the model of the noise that you're injecting?
Just random Gaussian noise with the ID entries. And I'm just adding the noise to the adjacency. Of course, it has to be symmetric and zero diagonal. So, of course, in practice, when I think of my graph as a metric space, for example, coming from a smooth manifold, there are some constraints on the noise, because if the points still reside on the manifold, there are many dependencies between the entries. But this is a very simplistic noise model. Any other questions? Yes, please.
What is the size of the graph here?
Well, here I randomize graphs from basically a few n equals, let's say, from 5 to about 50 or something like that.
50 is max?
Well, 50 is not a big graph, but otherwise it takes too much time because there are many experiments averaged here. But I guess it is large enough for some interesting phenomena to start happening already. Okay, so let's see what happens when we violate these friendliness assumptions. So I will assume now that my adjacency matrix doesn't have simple spectrum. So I will have the first eigenspace with some multiplicity m plus 1, then followed by second eigenspace with multiplicity m plus 2, m2 plus 1, and so on. So these m1, m2, and up to md will be counting how non-simple is each of the eigenspaces. So if mi equals 0, it means that I have a simple eigenspace. And I will sum them into some constant m. So it measures how non-simple is my graph. Okay? So then, of course, because once I have non-simple eigenspaces, there is no unique way of defining my eigenvectors. So then what shall I do with this demand of not being orthogonal to 1? It might happen, for example, if this is my eigenspace and this is the vector of 1s, it might happen that I will choose one of the eigenvectors that will be orthogonal to this by chance, right? So I will assume by convention that I will always avoid such situations unless, of course, the entire eigenspace is orthogonal to the vector of 1s. Then I have no choice. Then all my eigenvectors will be orthogonal to 1. So then it allows to distinguish between two situations. One situation is where the entire eigenspace is orthogonal to 1. I will call it hostile. Well, it will create some more degeneracy in my system of equations. And otherwise, it will be non-hostile. Okay? And I will count by this constant k the number of hostile eigenspaces. Okay? So then I can assign this m plus k as some sort of unfriendliness degree of my graph. And of course, if it's 0, my graph is friendly, as in the previous discussion. Okay? So then it's very easy to show that symmetric graphs, meaning that graphs that have non-trivial automorphisms with L non-trivial, such non-trivial automorphism, will have this unfriendliness degree at least of size L. And the argument is very simple, very similar to what we showed in the asymmetric case. So then we showed that for any non-trivial symmetry, there exists some eigenvector ui such that pi ui, distinct from ui, will be an eigenvector of the adjacency matrix corresponding to the eigenvalue lambda I. And if ui belongs to a simple eigenspace, then of course we only had a difference by sign, plus or minus 1, and we showed that ui transpose 1 was 0. Okay? And this basically means that each non-trivial symmetry will increment by 1 either k, if my eigenspace is simple, or m, if the eigenspace is not simple, or it might even happen that both are incremented. Actually, I don't have a specific example, but at least in theory, nothing prevents for this situation to happen. Yes, please.
How do you define, say you have a complete graph, right? How many symmetries would it have?
Well, then any permutation will be a symmetry. So if everything is connected and you're assuming the same weights on the...
Then you will have a factorial.
Yes.
I mean, isn't that your unfriendly degree be more than factorial?
Well, so in that case...
It cannot be more than that.
Well, I need to think about it. But basically, my argument is that the more non-trivial symmetries I have, the bigger is the bigger is this degree, the bigger is the degeneracy of my system. So going back to the optimality conditions that I had, basically I had these two equations. One was basically this first order optimality with VI's denoting the projections of the constant vector on my eigenvectors. And again, I'm assuming that I'm avoiding these situations. And the other one was the row sum, the unit row sum condition. So I can split these equations into a system of equations for each row of f. So let's call it fi, this vector of n elements. So I have, for each I have n such system, each system containing n plus 1 variables and n plus 1 equations. And some equations might be linearly dependent. Okay, so I have n plus 1 equation and n plus 1 variables. So let's see what happens when I have unfriendly graphs. So let's distinguish between two cases. So if I have a non-hostile eigenspace, then I know that Vi is distinct from 0, and by the argument we had before, I can say that gamma I will be equal to 0. So I can eliminate this second term, and I have now n unknowns with n plus 1 equations, but this matrix actually has a lot of basically missing equations. So the way it will look like, I will have lambda I minus lambda 1 squared. So this is entry 1. Then until entry I minus 1, I have lambda I minus 1. And here I will have a block of zeros of size mi or mi plus 1, mi plus 1, right? This is the dimension of my eigenspace. And then again here I will have non-zero entries, plus this additional linearly independent equation that has the vector v. So the bottom line is that my system is rank mi deficient. Okay? If I have multiplicity of mi plus 1 in my eigenspace. Now, in case of hostile eigenspaces, I will have Vi equals 0. So this means that I cannot determine gamma I, so it will remain as a degree of freedom. So I have n plus 1 degrees of freedom, and the same situation in this matrix. So this means that I'm mi plus 1 rank deficient. If I now sum all these contributions, remember I have n such systems. So basically, this system of equation that tells me what the solution has to satisfy is rank m plus k deficient. So basically, this unfriendliness degree of the graph tells me the dimension of my solution space of the convex relaxation. And if the dimension is non-zero, I might be getting some solutions that unfortunately will fall or might fall into wrong Voronoi cells and give me permutation matrices that are not isomorphisms. Okay? And of course, the actual solution that I'm going to get will depend on the algorithm that I'm using and on the initialization, which is basically a question of luck. And I can here either proceed by actually showing that for a sufficiently large m plus k, this will necessarily happen, that basically there will necessarily be some solutions that belong to wrong Voronoi cells. But this, of course, doesn't have a lot of practical value because eventually I want to solve this problem. So what I will try to do instead, I will try to show how to make this system full rank again. And here I will show a very almost trivial way to do it, but it leads to some thoughts of maybe some other ways, some more intelligent ways of removing this deficiency. So let's try to add some side information. And this is, again, something that is very frequently done in these practical graph matching problems. One of the ways is to add seeds. And seeds are known correspondences between graphs. So for example, if I have one graph and another graph, I can say that this vertex is known to correspond to this vertex. And by the way, it doesn't necessarily need to be vertex-wise correspondence. I can say that I have some blob corresponding to another blob. Or in general, I have sets of corresponding functions. Okay? So I can think of these functions as vectors. So I will have a matrix. Each column in this matrix will be a function on one graph, and I will have a corresponding matrix D with corresponding functions on the other graph. Okay? And let's say I have Q such corresponding functions. I will call them seeds. If I now transpose this matrix, I can think of it as vector-valued attributes that I'm assigning to each vertex. So each row in such matrix will be a Q-dimensional vector that I'm assigning to each vertex of the graph. And of course, I would like these C and D to be consistent with some preferred isomorphism. I have many isomorphisms because the graphs are symmetric, but I would like C and D to be consistent with one of them. Okay, so again, you can think of columns of C and pi star D as corresponding functions, or rows of C and pi star D as corresponding attributes. Okay, so now if I get back to the convex relaxation, I can add a term here that penalizes for the disagreement of these seeds or attributes. So you can think of it as penalty on attribute disagreement, or as a soft constraint version of seeded graph matching. So instead of putting PC equals D as a hard constraint, I can put it as a soft constraint. And this is something that is very frequently done. Of course, the more seeds you put, the easier it will be to solve the problem. But usually seeds cost you something to obtain. Like if you think of matching, for example, brain networks, these seeds come from an expert looking at the graphs and manually marking points. And let's say if each such point costs you $1, you want to minimize the number of such known correspondences. Okay? Well, actually now the argument will be very simple. So this looks quite unnice, but the idea is that I can actually formulate a set of constraints that my matrix, say D, has to satisfy in order for the system to become full rank again. So instead of going through these details, I will show you just the argument, and basically the rest will be just technical details. So as the input, we have two graphs, A and B, again related by many isomorphisms, but one of them is pi star. And I have these attributes, C and D, also consistent with this isomorphism pi star. Okay, so basically I would like now to add these C and D to disambiguate symmetries. And we have this convex quadratic program with positive mu. And the global minimizer is of course pi star, because if I substitute pi star here, I will get 0 in the objective. Again, I can reparameterize it in terms of Q equals P pi star transpose, as we did before. And the global minimizer will now become Q equals I. Basically, it is equivalent to assuming that the two graphs have the vertices numbered in the same way. And I would like to show that this minimizer will be unique. So again, if I get the first order optimality condition, now this term, actually these two terms, one linear term in Q, another one is a constant, will be added to the Lagrangian. Okay? And again, the pseudo-stochasticity constraint remains. I can again reparameterize this in terms of my matrix F. So what I will have here is a linear term in F that is multiplied from the right by this G. And this matrix G, you can think of it as the Gramian matrix of the attributes parameterized in the eigenbasis of my adjacency matrix. But this matrix, of course, is positive semi-definite. So adding attributes or seeds will usually increase the rank. So the rest, all the rest is just technical details, how to make sure that I'm adding the minimum number of constraints to just fill in the missing, basically just to eliminate the null space of my system. Okay, so there will be a distinction between hostile and non-hostile eigenspaces. So this is an experimental evaluation on 1,000 symmetric graphs with different number of vertices and different types and number of symmetries. And of course, this is a very limited experiment. I was able to only to randomize geometric graphs that come from some distance function. So of course it will be interesting also to test it on some other types of graphs. But basically what I'm plotting here on the horizontal axis is the ratio between the number of seeds satisfying these conditions that I'm adding divided by the number of non-trivial symmetries. So when this ratio is 0, it means that I'm solving the original relaxation without any seeds. And actually you can see that the success rate here will be very small, just to visualize that in many cases you are going to get a solution that falls into the wrong Voronoi cell. But when I'm adding the number of seeds which is equal to the number of symmetries, basically I'm completely disambiguating this system. I'm making it full rank and with probability 1, basically. At least in this experiment I'm getting the correct solution. Okay?
Is this for the optimization that you studied, or the original optimization that you showed us at the very beginning with the additional constraints?
No, so it's without the additional constraints. It's the affine space.
It's the affine one?
Yes. Okay. So and this actually brings a few interesting questions that have some practical consequences. So how exactly to choose the relaxation space? It looks like some constraints, like this set of constraints, looks like they're unimportant. We didn't use them anywhere. And actually, if you try adding them in practice, I haven't seen any empirical evidence of their usefulness. Now, regarding the non-negativity constraints, actually, there is both empirical evidence of their usefulness, and also you can show there is a recent result by Guillermo Sapiro and Marcelo Fiori that took our friendliness condition, and they show that if you put non-negativity constraints, you actually remove 1 degree of freedom from the system, and you can actually show that you don't need this condition on the eigenspaces non-orthogonal to 1. Instead, you can put some much easier condition on the number of non-zero elements in the eigenvectors, which is quite surprising. But if we get rid of these constraints, basically, does it have practical consequence in actually solving the optimization algorithm? Because you don't have overlapping constraints anymore. Maybe it can lead to some either distributed optimization algorithm or something that can work better in practice. Also, of course, all this analysis was very naive. We are not using any kind of geometry that actually characterizes the graphs. For example, if we are assuming that these are metric spaces, the matrices are metric, they obey the triangle inequality, they are coming from a low-dimensional space, maybe a smooth space with bounded curvature. Can we actually make use of these to either make stronger statements about the applicability of the convex relaxation, or maybe do a better relaxation that will work, at least for these kinds of graphs, for a larger family of such graphs? Also, one thing that I think, at least this way of thought suggests, and this relates to what I was saying about random graphs. So it is very hard, and probably you will argue about any suggestion that I can make about some natural distribution of graphs. But it would probably be much easier to agree about reasonable models of noise that I'm adding to my graphs. So can I actually take adjacency matrices that are unfriendly, and I know what are the eigenspaces that cause this unfriendliness? So can I actually try to break these symmetries by introducing some specifically designed low-rank noise that will only affect those nasty unfriendly eigenspaces? So by this I will break my symmetries, so the matrix will become friendly again. Will the relaxation still work? Because if this is true, then I can say that even if you are giving me graphs that are not amenable to relaxation because of this unfriendliness property, I can add a little bit of noise to the matrix, and with probability 1, they will become friendly and will become amenable to relaxation. And this is sort of way of thinking along what, for example, Dan Spielman showed for linear programming and simplex. Simplex is known to work very well in practice, but there are some linear programs that result in exponential time, exponential complexity of simplex, but he showed that if you add random Gaussian perturbation to such problems, then with probability 1 simplex will converge in polynomial time. So can we do something similar here for convex relaxations of graph matching? Because it looks like, at least from empirical evidence, that despite of the theoretical complexity, these problems are not so hard. So can we make some theoretical guarantees on modifying the problem a little bit and making them necessarily simple? And then another problem that is very interesting for some practical applications is actually not finding just one of the isomorphisms, actually enumerating and finding all of them. If you have, for example, a symmetric graph, I can be interested in finding all automorphisms of this graph and enumerating them and maybe finding some approximate automorphism up to a certain constant. So whether can we modify these results to obtain guarantees on an efficient algorithm for enumerating all automorphisms. Okay. I think I will stop here. Any questions? Please.
There's a huge literature on graph isomorphism, and it seems like you didn't touch on very much of it. And I was just curious, I mean, for instance, unique eigenvector values. That goes way back to the 70s or something like that.
Well, again, I'm not.
And there was all kinds of color refinement algorithms, which you didn't talk about, or bounded degree algorithms.
Yes.
It goes on and on. I mean, it was just huge literature.
Of course.
So like, it would have been interesting to compare known literature on isomorphism with your stuff, right? I mean,
of course. So I'm not arguing that. Probably this problem is studied to death, and not only results related to this particular formulation, but there are many formulations of the problem itself. Like, for example, this quadratic distortion is something that is used in practice for some kind of application, but there are many other formulations, like, for example, trying to minimize the edit distance between graphs and things like that. And there are also some theoretical results that are useful. And of course, for many types of graphs, like you are saying with bounded degree and graphs with simple spectrum, there is probably good theory. But at least what I discovered in practice, and again, I might be missing some amount of literature, that the constants on there, so there are even linear or almost linear complexity algorithms, for example, for bounded degree, but the constants there are enormously high. And of course, depending on the degree, but if the degree in a practical graph, let's say, exceeds 4 or 5, then these algorithms will become completely impractical. There will be like constants of millions or maybe even more.
Are you sure?
At least I've seen some results. I'm not sure how up to date they are, but the constants there look like completely unreasonable. And in fact, people don't use them in practice probably for this reason.
Because I don't understand why things work like that. But yeah, they require you to do group theory, but I don't think that was, is that really true? Because, I mean, like the color refinement algorithms, they work just very well, right? I think.
Can you give me references to?
Sorry?
Can you give me references to this particular?
Sure. I mean, there must be 100 references, right? I think there's a whole books on it.
Okay.
We can talk about that. Because the obvious thing is you wanted to make sure that your two graphs, the eigenvectors are not, are distinct, are all orthogonal to the all ones. But you could do that trivially by saying, well, clearly some vertex over here has to be mapped to someone over here, and if I'm willing to pick that and then go from there, then by then all the eigenvectors will have that property, right?
Yes, of course. But if you have simple spectrum, we can just take one of the bases divided by the other one, and you will get the permutation up to a sign. If you remove the sign, you get the permutation. Probably interesting phenomena happen when you don't have simple spectrum.
Right. I mean, but then there's all kinds of work on all that, right? I mean, that was a classic studied problem.
Well, I will be very happy to educate myself about this. But maybe the applied community can benefit from these results if they lead to something practical.
You have the combinatorial characterization of friendliness.
What do you mean by a combinatorial?
So you have the spectral characterization, like you have the spectral definition. Can you like state a combinatorial condition on your graph that will imply friendliness?
Well, at least I didn't think in this direction because I wanted to characterize the graphs in some way that is easy to check. But probably you can make some statements. Yeah, I don't have any results that I can show, but I'm sure you can make some statements. Like for example, this orthogonality to or non-orthogonality to 1 obviously excludes regular graphs and things like that.
Okay.
So I don't know what is the combinatorial characterization of a simple spectrum, for example.
I don't know.
And it probably would be interesting to relate this characterization to the properties of the Laplacian. Because if you relate to the properties of the Laplacian, then you will be capable of stating something about the properties of the Laplace-Beltrami operator if you assume that your graph is sampled from a manifold.
So